Students, today we're going to talk about winds. It's a good day to talk about winds because right now there's a hurricane down here in the Gulf of Mexico. And right now it is strengthening. It's going over very warm water. The Gulf is at 90 to 95 degrees right now. Lots of condensation is happening. When water goes from a gas to a liquid, when it condenses, remember, it releases energy to the atmosphere, and that provides the energy for the next strengthening of that hurricane. And it just keeps feeding itself and feeding itself until it hits land when it begins to weaken. This Hurricane Laura is about to hit Texas, Louisiana area. We don't know exactly what the outcome's going to be, but this Winds Over America map shows you what's happening right now in the winds. Fortunately for California right now, who are having wildfires, the winds over in California are very, very weak. 0.3 miles per hour, 3.6 miles per hour. Thankfully, they're not getting 70, 80, 90 mile per hour winds. Now, winds are so interesting. Why is it usually windy when you go to the beach? Did you ever notice? You'll be somewhere and then you'll decide, I'm going to go to the beach, and wherever you were isn't windy. And when you get to the beach, there's a wind. It's called a local wind. There's either a sea breeze or a land breeze at the beach. Local winds can also be things like the Santa Ana winds, which are a big reason why California has those horrible, horrible wildfires right now. It's a local wind because there's mountains and valleys, and because there's mountains and valleys, there's differential heating, and that leads to winds. We're going to do a very quick experiment, and we're going to use a light. I've got a heat lamp, and I've got a 25-watt bulb. These are going to represent the sun. Now, the sun is always the same sun, but why is it that in winter, if the sun's out all day, it barely warms us up? In summer, if the sun's out all day, it really warms things up. We'll learn about that in seasons. Let's just say we're going to represent the summer sun here and the winter sun here, but remember, in reality, the sun is the same. There's something about the way it's hitting the earth that causes it to have a different effect in winter and in summer. And again, we'll learn that in seasons. So I've got the sun. I've got water here. That would be representing the water at the beach. And I've got sand, and that would be representing the sand. So we have another model. In earth science, we use models all the time because it's really hard to bring a volcano into the classroom. It's hard to bring a river into the classroom, or a lake, or a beach. But we can make models in earth science and do a lot of earth science using models, like we have in a lot of our other lessons. So I'm going to plug these in. First, I'm going to tell you that the water here is at 23 degrees, and the sand here is at 22 degrees, which is about room temperature right now. This is at 22. And the water is at 22. I'm going to turn on the sun. So the sun is rising. We're going to go through a pretend day. Okay, and if you look on your data sheet for the winds, the sheet that you're going to be working from, you have a nice data sheet. And we're going to go through the course of a whole day. The sunrise, morning time, afternoon time, sunset, and then nighttime. So every 5 minutes, we would be reading the temperature for 30 minutes. At 15 minutes, we're going to turn off the light and get some data. Get data for the nighttime. Now, we're just going to leave this for a minute and then come back to it and see how temperatures have changed. I just want to give you an idea of how to do this in your classroom. Why is it windy at the beach? That's the question we're trying to answer. And again, I want you to answer that before we do anything, before you look at anything more in this lesson. Why do you think it's windy at the beach? This is going to be your reflective journal question for this lesson. Okay, so let's see if there's any changes so far. Not quite. So what we're going to do is we're going to go ahead and look at this program called WINS. All right? And there's a lot of questions on your data sheet that go along with this program called WINS. And I'm going to turn this background off. A lot of questions that go with this. The first few questions are just talking about what do some of these symbols represent. Okay. And there's a question, what are these map symbols? It says that the H stands for a high pressure system, and the L stands for a low pressure system. The yellow lines are lines of equal pressure, or isobars. The wind arrows show wind speed, so the longer the arrow, the faster the wind is at that point. The soap bubble, these just move in the direction of the wind. They move. In the northern hemisphere, the winds around a high pressure system will move in a clockwise direction. You may have noticed that on the winds over America. In the northern hemisphere, the winds over a low pressure system will move in a counterclockwise. Right now, down in Texas, Louisiana area, they have a very low pressure system, and you've got huge clouds and a very severe storm right there. Okay, the wind vane is going to tell us the speed of the wind. The barometer is going to tell us what is the air pressure at that time. Barometer measures, theoretically, a column of air from the Earth all the way to space and tells how much does that weigh, how much does that column of air push down on a liquid that's in a tube. It's a very interesting weather instrument. Okay, now, another question on your sheet talks about what happens when we change from the northern hemisphere, which is where we're at, to the southern hemisphere. If you notice right here, you see the winds showing this movement into the low in a counterclockwise direction. Let's change to the southern hemisphere, and let's see what happens. The exact opposite happens in the southern hemisphere. We've got counterclockwise into the high and clockwise at the low. The winds move in opposite direction in the southern hemisphere. I'm thinking most of you are going to be teaching in the northern hemisphere, so we'll stick to the northern hemisphere. Your next question says, what happens if the Earth stops spinning? Okay. Besides the fact that we are going to be in very bad, shape if the Earth stops spinning, what happens with the winds is instead of having this counterclockwise into the clockwise out of the high and counterclockwise into the low, you get this going straight from the high to the low. And that's due to something called the Coriolis effect, which is a really interesting phenomenon because the Earth is spinning. When we do our oceans lesson, when we do density, you're going to see that the Coriolis effect has something to do with how the currents go. You'll see that currents in the northern hemisphere move in a circle, and in the southern hemisphere move in a circle. So this stopping the Earth spinning simply means instead of having these winds going in counterclockwise and clockwise directions, they would go straight from the high to the low. Okay? let's get the Earth spinning again. And we're in the northern hemisphere. And the next question says, what happens to the direction and speed of the winds if you increase the air-earth friction? Let's say that a wind is going across a calm body of water. There's really no friction to slow that wind down. And a lot of you in your initial answer to why would it be windy at the beach, you might have said it's windy at the beach because it's a flat surface. And that's really not the true answer, but after our instruction, you're going to be able to give me the scientific answer to that question. Okay, so what happens if you increase the air-earth friction? Right now, the air-earth friction is weak. Okay? And because it's weak, we have very fast winds. In fact, let's take our weather vane and let's see how fast these fastest winds are. 45 miles per hour right now. Now, if I change this to strong friction, instead of going over a nice calm body of water or a grassland, now they're going over forests or buildings. The wind is still moving out of the north, but instead of moving at 45 miles per hour, it's now 13 miles per hour. So if you think about this, think about like if I rolled a marble along a nice flat floor, there would not be much friction. But if I rolled that marble along your grandma's shag carpet, that's a lot of friction. It would slow it down. Okay? So that's what it means, the air-earth friction. Funny story, when I brought my first daughter, when we were looking for colleges, we went to Central. And Central Michigan is like buildings in the middle of fields. And apparently it's very windy there often. And so my daughter said, Mom, I can't go here. My hair will never look good. And that was a proud moment as a mother. I thought, man, basing your college choice on your hair, you know, I felt really good about my parenting. Just kidding. I was just, it was very funny. As a parent, you got to have a good sense of humor. All right, let's go back to the friction of weak. And again, we see that 45 miles per hour. Now, if you notice, the high is here and the low is here. Let's see how fast the wind is close to the high, the wind. Oh, wow, close to the high, it's only 1 mile per hour. Let's see about close to the low. Close to the low, 6 miles per hour. So the wind speed is strongest where these arrows are the longest, right in between the high and the low. That's where the two different air masses, which we will have a lesson on air masses, interact. That's where they interact. Okay? So where they're interacting, there's a lot of action. Okay, so we've done all the questions on the first page. And then the next page says, place an H over Minnesota. Okay, so I'm going to go to Minnesota. And I'm going to show you a really interesting thing right here. And I'm going to run over here a second, grab a map. When you have to teach the states, there's a little man called Mr. Mimel. Okay? And Mr. Mimel helps your students learn 5 of the states, and he's actually got a plate of Kentucky Fried Chicken, so you could actually learn 7 states here. But if you see Mr. Mimel's hat, M, Minnesota, his face, I, Iowa, his belly, M, Missouri, his pants, A, Arkansas, and his boots, L, Louisiana. He's holding a plate of Kentucky Fried Chicken, so just a cute way to learn some of the states. plate of Kentucky Fried Chicken. All right, I digress. I know that's Minnesota because it's Mr. Mimel's hat. Now, the next direction says place an L over Georgia. So we're going to get that L, place it over Georgia. And then it says to take readings along that line. We're going to take 5 readings along that line. Okay. So our first reading is in Minnesota, and I'm going to look at the winds. And the wind is calm. The wind speed is calm. Wind direction calm. Location, Minnesota. Now let's take our barometer and let's measure the air pressure at that high. 30.06 inches of mercury. What that means is that column of air is going to push down on a bowl full of mercury that has a tube in it, and it's going to push that mercury up that tube to 30.6 inches. It's a very interesting way of measuring air pressure. Since this is a high pressure system and this is a low, do you think the number here is going to be higher than 30.06 or lower? Well, let's see. This is going to be position 5. Position 5 is going to be Georgia, and the air pressure in Georgia is 29.68. Okay. That would be position 5, Georgia, air pressure 29.68. Let's go right in between, and let's go to Illinois, and we've got Illinois 29.85. That would be position 3. Let's go to position 2, and let's go to Iowa, would be 30.04. And let's go to Tennessee. Tennessee would be 29.7. So you should see a decrease in the air pressure from the high to the low. I want you to fill in this chart with those figures. Now, we did not do the rest of the wind speeds, so let's go to Iowa again. And the wind speed in Iowa is 5 miles per hour from the northeast. And then let's go to Illinois again, and the wind speed is from the northeast, 63. I think I'm in a little different spot than the other measurement. Number 4, we're going to go to Tennessee again, and the wind speed is northeast, 12 miles per hour. And then we're going to go down to Georgia, calm and calm. So over the high and over the low, we have no wind. But where they're interacting, we have high winds. Okay? So winds, why is it windy at the beach? Let's take another look at our temperatures. The water here has reached 32. The sand has reached 56 degrees. The water is 32. The sand is 56. Let's see what our 25-watt bulb has done. The sand is at 29. The water is still at 23. Okay? This is called differential heating. Water absorbs heat much slower than sand. Sand absorbs heat much quicker. The thing about radiation, the thing about sand being a quick absorber, it's also very quick at releasing that energy. The quicker it absorbs, the quicker it releases. Water, on the other hand, absorbs very slowly, and so water will release that energy very slowly. And so the water and sand are not often at the same temperature. If they're at the exact same temperature, you're not going to have a wind at the beach. You're not going to have it windy at the beach. This one, we've got 29 and 23. There's still a difference. this is going to have a slight breeze. This is going to have a much bigger breeze because the temperature difference is much greater. And again, what is the reason for the temperature difference is differential heating. Water absorbs much more slowly. Water, to change the temperature of water, it takes a lot of energy. It absorbs slowly. It also releases slowly. The oceans are just a big, huge heat sink. They hang on to energy. And that's one other concern about climate change, is if the temperature of the oceans is altered because of melting glaciers, then the problem is that right now the ice reflects a lot of the heat that comes down from the sun. It just reflects it right back to space. No absorption. When that melts and now there's water, it absorbs that energy and it hangs on to it. It doesn't release it back out to space. So that's a big concern. And just recently they were saying that Greenland will never be able to replace. It's melting faster than the freezing happens in the winter. And so slowly there's less and less ice. There's still ice buildup in the winter, but the rate of melting is much outpacing that. So yeah. All right, let's turn off the lights. And we're going to see what happens when we turn out the lights. Let's go back to our program, get some more questions answered in the meantime. So we've answered number 7. It says, what happens to the wind speed and direction if you change your H and L from normal to strong? Right now, I have normal highs and lows, okay? All that would mean to make it a strong high and low would mean that the difference between the air pressures would be much greater, okay? Let's go to strong, okay? And let's just measure that barometer again. I think this was 30.06 before. It's now 30.21. And let's just go down to, let's get that weather vane out of there. The low is now 29.44. So there's just a greater difference between the pressure in the high and the pressure in the low. Now, we cover this high and low pressure thing in several lessons. So if you're worried about it, don't worry about it yet. We're going to look at it in a lot of different contexts. Look at these winds, however. Look at the size of the arrow. Let's take our little wind vane in here. The wind is now out of the northeast at 124 miles per hour. Okay? That's a very, very strong wind. Why is it a strong wind? Because the barometer here is very high. The air is very heavy. It's very cold air, I will just tell you. That a high pressure means cold air. A high pressure means the air is sinking. It's very cold, and cold sinks. A low pressure means the air is rising. So you could see, if you're measuring it by how much the air weighs when it presses on the mercury, you can see that if the air is rising, it's going to press down on that mercury less, and so you're going to get a much smaller reading. Now, these numbers aren't hugely different from one another, 30.46 versus 29.44. But look at the effect on the wind, okay? So what's the relationship between pressure and wind speed? Okay, you need to answer that question. It says, in general, where on the map is the wind the fastest? Remember, when they're interacting, that's where it's fastest. Between the high and the low, that's where it's fastest. And where was it slowest? Let's see if it's still calm over the high, or if it's still calm over the high. Slowest over the high and over the low. All right, so let's go to our next set of questions. What do the H's and L's on the maps represent? We've already kind of said that. Whoops. We've already answered that. I'm going to the last page. Okay? And on the program, we have the question of wind. So our first question, what is atmospheric pressure? Very simply, we're going to look at the actual definition. And like I said, it's the weight of a column of air stretching from the Earth to the atmosphere. Now, what do you think about the pressure on top of a mountain versus at the base of the mountain? How big is the column of air on top of the mountain? It's a much smaller column of air. So what would that mean about the pressure? Think about that. All right. What are high and low pressure centers, and where does the air entering a high and low go to? Okay, so let's go back to high and low pressure centers. Okay. Again, a high pressure center is where cool air is sinking. A low pressure center, warm air is rising. That's why normally whenever there's bad weather, it's associated with a low pressure system, because when warm air rises into the atmosphere, it runs into colder air. We've got the cold and warm interacting. We've got condensation. We've got energy released to the atmosphere, and that leads to a lot of the weather. Let's see, where does the air go in the low and the high pressure systems? This is just a nice depiction showing in the low, it's going to go up into the atmosphere. In the high, it's going to go down. And remember, in the northern hemisphere, it's going to go counterclockwise into the low. It's going to come out of the high in a clockwise way, but it's also sinking. And that's where we get these storms, and lots of things happen when we have the high and the low interacting. The more drastic the difference between the high and the low. We get tornadoes when there's super cold air and very warm air interacting. That's when you get a tornado. You get this very huge difference in their temperatures. Okay, number 4, there's 3 forces that determine the strength and direction of wind. And let's look a little bit at these forces. We have the pressure force, high pressure and low pressure, and like I said, the greater the difference, the greater the wind. And remember, high pressure means low temperature, low pressure means high temperature, so the greater the temperature difference, the greater the wind. So that's the one force. The friction force, again, we see, just makes sense. If a wind is going through a city and there's a lot of obstacles, that's going to slow it down. Now, the wind will always travel from the high to the low. It doesn't hit a building and then go back to where it came from. It just goes over the building, keeps going in that direction. And another thing, that winds are named by the direction they come from. So a north wind is coming from the north, going to the south. We like a north wind in the summer. We hate a north wind in the winter. It's just brutal. We love a south wind in the winter. South wind bringing nice warm air to us. So a north wind would go from north to south. Now, I mentioned before land breezes and sea breezes. Winds are named by where they come from. So a land breeze would go from the land to the sea. A sea breeze would go from the sea to the land. Okay, that would be. The third force is that Coriolis force, and that's the one that causes, instead of the wind going directly from the H to the L, it deflects it in the northern hemisphere, deflects it to the right out of the high. The southern hemisphere, it's exactly opposite. And that is just a huge story why it's opposite in each hemisphere. In the Coriolis force deflects the wind to the right coming out of the high, to the left going into the low. And so you'll see this very interesting pattern with winds. All right, let's look at our temperatures, see what's going on here. This water has cooled to 33. The sand is still at 50. This water's at 24. And the sand is still at 30. Eventually, things will cool down to room temperature. It's just a matter of time. I'm going to do a quick demonstration about the Coriolis effect, just to give you a very, very basic, very basic understanding. Okay? Why would things be opposite in the northern and the southern hemisphere? So the Earth moves counterclockwise. Okay? I'm going to put Ken on the equator, and for him, the Earth seems to move from his left to his right. Okay? I'm going to have him facing the North Pole. When I have Ken move and to the southern hemisphere and looking at the South Pole, the Earth's still moving the same way. But to Ken, now, the Earth seems to be moving from right to left. Okay? This is a very rudimentary, very simple understanding. Okay? It's amazing when you think about that the Earth is spinning, we can't feel it. But if planes and missiles, in fact, the way we discovered about this Coriolis force was in World War II when we kept shooting missiles and they were off by a little bit because the calculations did not include that the Earth had moved a little bit in the meantime. They were shooting them in a straight line to their target. But in the meantime, the Earth had moved a little bit. So then they started shooting them to where they predicted the Earth would move. And it was more successful. So it is true. On a very long, high fly ball, that it could be fair or foul based on that tiny little movement. It's got to be right there on the line. But the Earth could actually move the movement of the Earth while the ball's in the air could cause it to go fair or foul. But that would have to be Miguel Cabrera hitting a long, high ball that was right on the line. Okay, very rare. But anyways, just a little understanding of the Coriolis force. It is a very complex topic. Let's make sure we've covered everything. And of the three forces, the ones that affect the direction and not its speed, of course, the friction force affects the speed, and the pressure force affects the speed. The Coriolis force just affects direction. Okay, excellent. Let's look at this one more time, our temperatures. Not much change. Okay, this is down to 47, so it's gone down a little bit. 30 and 24 still. All right, that was just a simple experiment you could do in your classroom. Now, how are you going to present your why is it windy at the beach? You're going to do it in a very fun way. This is called a Freyer map. Okay? And these Freyers are like magic for the kids. Honestly, if you ever are just stuck with what you should do for a lesson plan, make up a Freyer map. It's simply a topic in the middle and a piece of paper which has been folded into fourths. Okay? In this case, your upper left quadrant, why is it windy at the beach? This is going to be your initial answer before instruction. Why is it windy at the beach? Below it is going to be your scientific answer after instruction. Up in this quadrant is going to be wind diagrams. Remember, the winds go from the high to the low. The high is the cooler. So in our sample with the water was cooler than the sand. Because the water's cooler than the sand, that's where the high pressure would be. So the water would be, the wind would be moving from the water to the sand. So if you look at this student has shown a little diagram here with an H and an L and shown the opposite in the lower hemisphere. Let's get a better diagram for you. Okay, let me draw one, okay? So let's say we had 50 degrees for the sand and the water was 33 degrees. And this was Celsius, okay? All right. Where is the high pressure system? Remember, high pressure, heavy air, sinking air. So this would be the high because it's colder. Low pressure would be the warmer air. In this case, when the water is cooler than the sand, we have a sea breeze. Okay. This column here, you are going to make a diagram of a sea breeze and a land breeze. Okay? So your paper's going to be in fourths. You're going to have winds in the middle because that's our topic. Now for a frayer, you could have anything in the middle. You could have my family. Or you could have, if you ever are just dying for a lesson plan, just have the students do a frayer. They love it. When you take a piece of paper and you fold it into fourths, it becomes a magical piece of paper. I'm not kidding you, okay? So this was going to be, why is it windy at the beach? Initial answer, this is scientific answer, okay? This is going to be your diagram. And this is going to be a personal story about wind. This is my favorite part of grading this lesson. I've had kids who had their grandparents buried in sand. I've had a student who on their first day of the job at a golf course left the door a little ajar, and of course a windstorm had to come that night. The whole shop was just everywhere. I've had students that were driving their car and huge wind, big tree comes. Student got their $20, heading to the store to buy mom something. $20 bill flies out of their hand, chasing it down the street. I love reading your personal stories about wind, and this student really got cute, making little envelopes. Made me a little picture in here. So this frayer, you can go as fancy as you want. You do not have to be this fancy and colorful. You can still get a good grade if yours is, more simple, but it's kind of fun, and it gives your students a chance to be creative in science class, which is awesome because some kids don't even get art class. So the frayer, this is called a frayer. This is going to be your assignment, okay, along with the questions that we answered.